Hello dear friends, I welcome you all for the lecture number 12 on Hammett linear free energy relationship. In this lecture, we will discuss about the steric parameter ES and delta. ES and delta. Now, now we have already discussed about the Hammett type Stark equation for the various aliphatic reaction. Various aliphatic reaction where we can calculate the reaction constant value of reaction constant for the various aliphatic reaction using the rate measurement and by using the substituent constant R for the R. Now this reaction shows the sorry. Now by using this equation, we have a straight line relationship for many aliphatic reaction. Now this reaction consider only the polar effect as the steric effect is cancelled out. And for many reaction using this equation, we have a straight line relationship for the many aliphatic reaction. It doesn't mean that the steric effect is absent in such a cases. Steric effect is absent in such a cases. It only means they do not change significantly during the reaction. They do not change the significantly during the reactions. But now some aliphatic reactions are there where we use this equation, and by using this equation, we plot a graph, and this plot shows the departure from the straight line, and this departure of the straight line is due to the presence of the significant steric effect. That is, reaction with significant steric effect shows the departure from the straight line, departure from the straight line, and therefore here uh, it is necessary to introduce this steric parameter. It is important, or it is necessary to introduce this steric parameter, that is yes, for a reactions of aliphatic substituent for the aliphatic compounds. uh, it is necessary to introduce the substituent constant where such a reaction shows the departure from the straight line. Now, how the value of this steric parameter is calculated? For this, they consider the acid catalyzed hydrolysis of aromatic ester, acid catalyzed hydrolysis of aromatic ester, which is nothing but this. Now, for this aromatic ester, acid catalyzed for the hydrolysis of for the acid catalyzed hydrolysis of aromatic ester, in such a cases polar effect is completely absent, and steric effect is also absent, because this polar effect is absent as we have a rho value is 0.03, which clearly indicate that the susceptibility of this reaction uh, towards this polar effect exerted by substituent is very small, or you may say that it is negligible. And at the same time, steric effect for this reaction is also almost zero, as this X is a far apart from this reaction center, and therefore as the both effect are absent, that is polar effect as well as steric effect, the various aromatic esters undergo the acid hydrolysis with almost same rate. But if we carried out the same reaction for the aliphatic esters or ethyl ester acid catalyzed hydrolysis, then we have a product corresponding acid. Now in this reaction, as we know that the rho value for this reaction is 0.03, indicating that the polar effect is almost negligible. Polar effect is almost zero. Now, if we carried out the series of uh, series of acid catalyzed hydrolysis of the aliphatic ester. Then we have a change in a rate constant, a rate constant. As this R it changes, the rate of reaction, the rate constant of the reactions are also changes. So it clearly means that the change in rate constant is clearly due to the steric effect, and by using the various by measuring the rate constant for the various aliphatic esters, we have we can calculate, and comparing that rate constant with this ethyl acetate, with this methyl acetate, which is considered as a standard, we have it, we can find out the value of steric parameter. So here let let have a third butoxide acid hydrolysis. And if we compare the rate of reaction number 1 with reaction number 2, this is reaction number 1 and this is reaction number 2, and by having the ratio of rate constant of reaction number 1 to reaction number 2, we have a value of es for third butyl group. We have a value of es, that is steric parameter for the third butyl. And uh, theoretically we can conclude that the rate of reaction number 1 will be the very much slower than reaction number 2, as in reaction number 1 there will be the huge steric crowding due to this third butyl group. And in this way by comparing the series of reaction or number of reaction, by comparing the number of reactions, we have a delta value for that particular substituent. So here is the chart for that particular value of es for that particular substituent. So we know that hydrogen is having the uh, comparatively methyl group, hydrogen is having the less steric effect or zero steric effect. So only the rate of ethyl format will be the more than the methyl acetate, ethyl acetate. Sorry, the rate of ethyl format will be the more than the ethyl acetate, and therefore in this case es value for hydrogen, for when r is equal to hydrogen each, when r is equal to hydrogen, we have a value of es is 1.24. But now, as we move from the more bulkier group than methyl, for example, methyl to ethyl, methyl to chloromethyl, methyl to, and so on. So, as the steric crowding increases, the value of that ES become more negative, more negative. Here, negative sign indicate that decrease in rate of reaction. Rate of reaction is decreases, and therefore it is shown by the minus sign. So this triethyl this group is having the very high value of ES, very high negative value of ES, indicating that this group is having the strong cause the more steric crowding compared to all these. So more the negative value of ES, more will be the steric effect caused by that particular group. So in this way, here we we calculated the value of ES by measuring the rate constant for rate constant acid catalase hydrolysis of aliphatic ethyl esters with a methyl ethyl acetate, and by comparing this rate as rate of for this acid hydrolysis, we have a value of ES. Now we can put this value of ES, and we can put this value of ES and can explain this departure from the straight line by departure of straight line, and therefore the equation now become. Now the top equation is now get modified. But before modification, there is a one more factor. There is a one more factor delta, which is to be introduced, in the Hammett type top equation. Now why there is a necessary, to introduce such a delta parameter in the Hammett type top equation? This is because the we here consider the effect of the R group in the reactant only. What about the reagent, steric effect of reagent? As for a particular reaction, the steric effect caused by the incoming reagent is also different. For a particular type of reactions, the steric effect is also changes. Steric effect is also changes as reagents of that particular reaction is changes. Okay, so I am highlighting here. It is found that in practice that the value of steric parameter for a particular group R differs to some extent from one reaction to another. Now, this is not altogether surprising, as both the local environment of R and size of attacking reagent will vary from the one reaction to another reaction. As we, as the reaction changes, the steric effect of attacking reagent is also changes. The steric effect of attacking reagent is also changes. It means that, however, that incorporating the ES into the Hammett type top equation, it is necessary to introduce the yet further parameter delta as a measure of a particular reaction susceptibility towards the steric effect. Now, what is this steric? So here the two steric parameters are introduced. This steric parameter ES is for the R group in that aliphatic reactions, and delta is for the reagent, for the incoming reagent or attacking reagent for that particular type of reactions of aliphatic compounds. Now, compare to this rho constant, this delta is a steric parameter which measure the reaction susceptibility towards the polar effect. Means here this measure, the sigma star measure the susceptibility towards the polar effect, and delta measures the susceptibility towards the steric effect. And the modify Hammett type Stark equation is log of Kr upon K methyl is equal to rho star into sigma star R plus delta into ES, and which can be determined experimentally. The value of E and delta can be determined experimentally. The delta parameter is given the value 1 for the acid catalase ester hydrolysis, acid catalase ester hydrolysis. If any reaction having the delta less than 1, if delta is less than 1, then it means that the uh, incoming nucleophile is incoming reagent or attacking reagent is having less steric effect compared to acid catalase hydrolysis. And if delta is having more than 1, then it indicates that the uh, uh, attacking reagent is having the more steric effect, compared to acid catalyzed ester hydrolysis. So in this way, this is the modified Taft equation, Hammett type Taft equation, which can be used for the uh, various reactions of aliphatic ester. Can be used for the various reaction of aliphatic ester. Here is the one example of delta. The steric parameter have an introduced in this way. The treatment can be extended to include the reaction of ortho-substituted benzene and derivative as well, and thus the acid catalyzed hydrolysis of ortho-substituted benzoamide. The value of delta is found to be 0.81. This is acid catalyzed hydrolysis of amide, ortho-substituted, ortho-substituted acid catalyzed hydrolysis. So for this reaction, delta is having value of 0.81. 0.81. So 0.81 means the small delta value. It should be note that this equation is not successful to quantify the ortho substituent effect. Ortho-substituent, when the ortho-substituents are there, then others, there are the other factors like hydrogen bonding, or due to the close proximity of this X group, it can have a various effect, and therefore this Hammett type Taft equation is only applicable for the aliphatic esters, and for the many orthoesters, or for many ortho reactions, this Hammett type Taft equation is not very successful. So this is all about the Hammett linear free energy relationship. Hammett linear free energy relationship. The best reference book or textbook for this is Peter Sykes. These are the two textbook you can prepare for this chapter, that is organic a guidebook to mechanism in organic chemistry, written by the Peter Sykes and Jonathan Clayton, the well-known book for the organic chemistry students, Jonathan Clayton and various and others. Okay, thank you.